Hello everyone, my name is Edgar Contreras. In this video we will review a few concepts to have a better understanding of first order systems and a method to fit their responses using first order systems with delay or dead time. We call a first order system to a system whose input or output equation is a first order differential equation. First order systems are an extremely important class of systems. Many practical systems are first order. For example, the mass damper system and the mass heating system are both first order systems. Higher order systems can often be approximated as first order systems to a reasonable degree of accuracy if they have a dominant first order mode. Most of the processes modeled using first-order systems are dependable on time, which makes their differential equations to be in terms of time variations. Therefore, their solutions normally are exponential behaviors depending on the time domain. However, it's important to note that for simplicity convenience, the functions are transformed to be in terms from the S-plane domain. Mainly because an advantage of the S domain is that using Laplace transform, you can convert time domain signals that include exponents to simple algebraic expressions in the S domain. In mathematics and engineering, the S-plane is the complex plane on which Laplace transforms are graphed. It is a mathematical domain where instead of viewing processes in the time domain model with time-based functions, they are viewed as equations in the frequency domain. However, this is our first order normalized transfer function form. K stands for our function gain or plant gain, and the constant tau is our constant time, our time constant. And this pretty much makes the system go faster or slower, and the constant gain makes the system response to change its amplitude. Now, a first order plus dead time or delay time is a simple approximation of the dynamic response, which is the transient or time response of a process variable to an influence. In first order plus delay time modeling, typically we consider that the influence has remained constant in the recent past and that the process variable had achieved a steady value. Then we consider that the influence makes a step and hold, then holds that new value until the process variable reaches its new steady state. The dead time represents the time duration after the influence changes during which the process variable does not change. First order plus delay time transfer function has the following characteristics. It has a constant gain, which again makes the response change its amplitude, and is the relation between the steady state output of our y-axis, which is our yf is our final y level, and our uf is our step input final level or steady state value, which it doesn't change on time. Here we subtract our starting point from our final point of y-axis, so we can have both changes. Here is yf minus the starting point and uf minus the starting point. The time constant tau, which is here, and the delay theta can be obtained by getting these two values. First, we measure the yf which is our steady state value for the response, and then we take the 63.2% of this value, and we can see it's around here. Therefore, the time, which is x-axis, says that the heuristic rule is that the time for the 63.2% change of the exponential behavior of our signal is going to be equal to our time delay and our time constant tau. And similarly, we get that for 28.3% of our final steady state value in y-axis. We locate this, and then we see the time, and that time is going to be equal to our delay time and our time constant divided by 3. Our settling time, tau, for first order plus dead time, it's similar to our over-damped response, which is around 4 times tau. The 98% means that the change from steady state is going to be a height of around 98% of YF. So that's the settling time for this. Now, our main case, it's going to be RC circuits. Why? Because another good example for a first order system is an RC circuit. The RC circuit has thousands of uses and is a very important circuit to study. Not only it can be used to time circuits, it can also be used to filter out unwanted frequencies in a circuit and used in power supplies, like the one for your computer, or to help turn AC, alternative current voltage to direct current or DC voltage. What are other applications of RC circuits? They are used in traffic lights, in pacemakers, audio equipment, and in places where signal filtering is needed. They can also be used as an integrator or differentiator. How do RC circuits look? Well, the simple RC series circuit shown here is driven by a voltage source. Because the resistor and capacitor are connected in series, they must have the same current I of t. For the sample circuit, what follows next, we have the following equation. The resistance through the whole circuit is the total resistance. Then, to find the voltage across the resistor, we use Ohm's law for a resistor device, which is the following equation, which is equation 1, which is the voltage equals to the resistance times the current. Now, generating current through a capacitor takes a changing voltage. If the capacitor voltage doesn't change, the current in the capacitor equals to 0. Zero current implies infinite resistance for constant voltage across the capacitor. Now, we substitute the capacitor current I of t, which is the following, is the capacitance multiplying the change in voltage over time. Then we may substitute these values of equation 2 into equation 1 and get equation 3, which is our voltage in the resistor. And then we use Kirchhoff's voltage law, which says that the sum of the voltage rises and drops around the loop of the circuit is equal to 0. Therefore, we have the following equation, which is equation 4. In this case, we say that all the voltage is going to be constant, which is similar to a mass balance but with electricity. And then we substitute the voltage in the resistor into the Kirchhoff's law as follows. We get a differential equation, which is a first order differential equation, where the unknown function is the capacitor voltage. Knowing the voltage across the capacitor gives you the electrical energy stored in a capacitor. In general, the capacitor voltage is referred to as a state variable because the capacitor voltage describes the state or behavior of the circuit at any time, which is very suitable to model using a first order transfer function. However, as we mentioned before, it's more convenient to transform our time domain function into the S domain for simplicity as shown in equation 6. Using simple algebra shown in equations 7 and 8, we get our final first order transfer function form as shown in equation 9, where we can see that our gain constant K is equal to 1, and the parameters we are going to use for our model are the following: a resistance of 10 kilo ohms and a capacitance of 100 microfarads, which give us a time constant tau of 1 second, and again we already have our gain. What follows next is we're going to fit our first order model using SIMULINK. Now we're going to learn how to fit the first order system using a first order system with delay time. To do this, it's important to open a new Matlab script window, and then we click on SIMULINK button, and then we go to the blank model tab. We click on the create model. As I already did this, I'm going to skip this step and just close this window. Once we click on the create model button, we get a workspace that looks like this. In order to create the model for our first order system, which is the voltage transfer function we developed earlier, we click on library browser and drag the step, transfer function, scope, and transport delay icons to the workspace. Then I set the step parameters, which is a unit step, which is going to be our time deviation variable, and we set a running time enough for our system to reach steady state. We run the simulation, and once the simulation is complete, we double click on the scope module. In order to get these measurements, we click on the cursor measurements, and we are going to get these lines displayed. How this works is we were required to calculate the 63.2% of the steady state value, as well as the 28.2%. However, we need to measure our steady state value and the starting point for both our input and our signal. Here we choose our function, and we can place to the last point of operation from our function, which seems to be around 1. Then we place the first cursor to starting point of 1, because it was our time deviation, and we get that the value is 0. Therefore, the change of our signal on the y-axis, which is our voltage, which is our process variable, is equal to 1. Now, we measure the step and we check for the starting point, and we get that it's equal to 1 minus 0. Therefore, we proceed to calculate the gain as follows. We get that the gain K equals to the change of the steady state output over the change of our input, which is 1 minus 0 over 1 minus 0, which is 1. Now, we have to measure 2 times. One at this point, which is the 63.2% of the steady state value minus the deviation variable or starting point plus the starting point, which both are equal to 0. Therefore, we only have to measure the times at levels of voltage of 0.632 and 0.283 as follows. I already calculated these times earlier for time convenience, so I'm going to place them, the cursors, in these values, which are 1.337 and 2.002. For our transfer function, we get that we actually have the 28.3% and the 63.2% with this time. However, we still need to subtract our deviation variable, which is 1, as we saw earlier here. In this case, it's this one. And once we solve the system of equations, we get that the time constant tau equals to 0.9975 seconds, and the delay time equals to 0.0045 seconds. Now, in order to check our model fitting, we go back to our workspace and we set the parameters of this transfer function using constant tau and the gain, this is our time constant. So we already have our gain set as 1, so we already have to use this value here. We change the denominator coefficients as follows, which this is our tau, which is our time constant. We apply the changes, we click on OK, and we can see that now our transfer function looks like this. In order to see our transport delay, we have to input the value gotten here, which is 0.0045 seconds. 45 seconds. Apply. Click on OK. Delete this. And change our scope ports to 3. We connect this here. This is only to verify our model fitting adjustment, and we run the simulation. As we can see, our model has a quite near perfect fit Actually, the model we fitted is the orange signal, and it reaches the same steady state value as our main transfer function with the same input. Therefore, we can say that this fitting method is quite accurate for first order systems.